Welcome to this explainer. Today, we're doing something really cool. We're going to act like a microscopic lens and a highly sensitive magnetic field detector to map out the hidden forces that literally power our entire modern world. You know, the concepts we're unpacking today? They surround us every single second, yet they're completely invisible to the naked eye. So we're going to break down exactly how the smallest possible particles in the universe interact to create the massive sweeping forces of electricity and magnetism. Let's get right into it.
Here's our roadmap for mastering these invisible forces. We'll start with the anatomy of charge, move into flow with AC and DC, uncover the electrical push, known as EMF, reveal the secrets of magnetism, and finally, look at what happens when these forces collide in electromagnetism. So, Section 1, the anatomy of charge. To really understand this, we have to step right inside the atom. When we peer inside a single atom, right there in the dense center, the nucleus, we see positively charged protons hanging out with neutral neutrons. Orbiting on the outside, kind of like a frantic little solar system, we have our negatively charged electrons. Now here is the absolute fundamental rule of the universe that governs everything we're going to talk about today. Opposite charges attract and like charges repel. It's this constant push and pull that sets the stage for literally all electrical phenomena.
But not all materials handle these charges the same way, right? Crucially, our whole modern world relies on whether a material is a conductor or an insulator. Materials like metals or molten ionic substances are conductors. Why? Because they contain charged particles, specifically those free electrons we just talked about that aren't tightly bound to their individual atoms. They're totally free to move and carry a charge. On the flip side, insulators like plastic or glass do not have these free charge carriers. Their electrons are locked down tight, meaning electric charge simply cannot flow through them.
Let's see what happens when a negatively charged body is brought near a metal conductor. Because of that repulsive force we just mentioned, the free electrons in the metal literally physically migrate away. They just run for the hills. But in an insulator, because those electrons are locked in place, they can't leave their atoms. They just kind of shift slightly to one side inside their atomic structure. And honestly, this mechanical difference is exactly why the wires in your house are made of copper, but they're wrapped in a safe layer of plastic.
Okay. Section 2, flow, alternating and direct. Now that we've got charges, let's get them moving.
Our first type of flow is direct current, or DC for short. This is what you get from everyday cells and batteries. It's super straightforward because the flow is essentially a one-way street. Mechanically speaking, those actual negative charges, the free electrons, flow continuously in one single direction. They travel from the negative terminal of the power source all the way around the circuit to the positive terminal. Simple enough, right?
Now, if we graph this over time, there's a really striking visual difference between direct and alternating current. For DC, the graph is a steady, flat, continuous line. It never crosses the zero mark, meaning the direction never, ever changes. But for alternating current, or AC, the graph constantly waves up and down, crossing that axis over and over. That wave perfectly maps how the electrons in an alternating current are quite literally changing direction, just bouncing back and forth continuously.
To keep this all straight, just think about the power sources. Direct current gives you that one-way flow from a battery's distinct positive and negative terminals. Alternating current, on the other hand, is what's generated by massive turbines for your home's mains power. It constantly changes direction and uses two identical terminals.
Moving right along to Section 3, the electrical push, EMF. Let's talk about what actually gets these electrons moving.
Current is fascinating for sure, but those electrons don't just magically decide to flow on their own. They need a very specific force, an energetic push, to drive them all the way through a circuit. And that brings us to a concept known as electromotive force, or EMF. Whenever charge moves around a complete circuit, electrical energy has to be transferred to those particles by a source, like a battery. So EMF is defined simply as the electrical work done by a source in moving a unit of charge entirely around a complete circuit. For instance, a heavy-duty car battery provides a powerful push of 12 volts.
Mathematically, we can break this down to see exactly what a volt actually is. The electromotive force, E, which we measure in volts, is precisely equal to W, the work done or energy transferred from the source, measured in joules, divided by Q, the electrical charge measured in coulombs. So if you want to sound really smart at your next trivia night, just remember, every single volt is simply 1 joule of energy pushing 1 coulomb of charge.
Now, let's see how this concept builds. While EMF is the total push provided by the source for the entire circuit, a voltmeter is usually set up to measure something called potential difference. What's the difference? Well, potential difference looks at the exact work done by a unit charge as it passes through just one specific component, like a single resistor or a light bulb, transferring its electrical energy into heat or light. So EMF is the whole trip, while potential difference is just one stop along the way.
All right, Section 4, the secrets of magnetism. Time to map out some completely invisible fields.
Because magnetic forces are completely invisible to us, we have to rely on some clever experimental tricks to map them out in the real world. You can actually do this at home. Just place a simple plotting compass next to a magnet, mark a dot exactly where the needle points, and then repeatedly move the compass tail to that new dot. By doing this step by step, we can physically trace the exact path of an unseen magnetic field.
And if you follow those compass steps carefully, you'll perfectly trace out a pattern that reveals the true strength and direction of the field. There are two huge takeaways here. First, the arrows on these field lines always travel strictly from the North Pole to the South Pole, never the other way around. Second, notice how the lines bunch up super tightly near the poles? In physics, the closer the field lines are to one another, the stronger the magnetic force is in that specific area.
Now there's a critical difference in how materials interact with these fields. Non-magnetic materials, like plastic, they couldn't care less, but magnetic materials behave in two distinct ways. Permanent magnets, which are often made of steel, produce their own continuous magnetic field. They are always on, which makes them perfect for something like a compass. On the other hand, temporary magnets, often made of soft iron, only become magnetized when they're placed inside an external field. The second that field is removed, they lose their magnetism. And this incredibly handy property is what allows us to build powerful electromagnets that we can control and turn on and off at will.
So, why does this happen? The secret is hidden in microscopic magnetic domains inside the metal. Picture an unmagnetized material as having domains pointing in every random direction, just totally canceling each other out. When exposed to a magnetic field, they all snap to attention and align. But here's the kicker. A temporary magnet's domains will immediately scatter back into random chaos when the external field drops. A permanent magnet's domains, though, they physically lock into this unified, powerful alignment permanently.
And finally, Section 5, when forces collide, electromagnetism. This is where it gets really good.
We begin with the motor effect. Up until now, we've looked at electricity and magnetism separately. But guess what? A moving electric current naturally generates its very own magnetic field, forming concentric circles right around the wire. Because of this, if you place a live current-carrying wire inside another external magnetic field, those two distinct fields are going to interact. They literally push against each other, exerting a physical, perpendicular force that makes the wire move. This right here is the fundamental secret behind literally every electric motor on Earth.
And the coolest part is, we don't even have to guess which way the wire is going to jump. We can predict it exactly using Fleming's left-hand rule. If you hold out your left hand and align your thumb, first finger, and second finger at rigid 90-degree right angles, you create a perfect 3D model. If your first finger points in the direction of the external magnetic field and your second finger points in the direction of the current, your thumb will reliably point in the exact direction of the resulting physical thrust or force. It's like a built-in physics cheat sheet right on your hand.
Now, brilliantly, this interaction also works in complete reverse. Just as an electric current can create physical motion in a magnetic field, physical motion in a magnetic field can create an electric current. We call this electromagnetic induction. If you mechanically push a permanent bar magnet in and out of a wire coil, that shifting magnetic field forces the free electrons in the conductor to move, inducing an electromotive force. You are literally generating real electrical current out of pure mechanical motion. It's absolutely wild. So, we've traveled from the microscopic attraction of protons and electrons all the way up to the induction of energy that powers entire cities. As we wrap up this explainer on the hidden building blocks of our world, I want to leave you with a question to chew on. If moving electrons create magnetic fields and moving magnets generate electric currents, are they really truly separate forces, or are they just two interconnected sides of the exact same invisible reality? It makes you wonder what other invisible realities might be intertwined right in front of our eyes, just waiting for us to map them out. Thanks for joining me, and keep questioning the world around you.